The Big Bang is the most accepted theory that our universe was created from a singularity. The Big Bang was a rapid expansion of space-time from an extremely hot, dense state about 13 billion years ago, giving rise to the universe as we know it. But here is another meta question. Why is there a Big Bang? What existed before the singularity? No scientist can answer this question. If the universe is a program, it's easy to understand. We know every program has a burst time. When you turn on your computer or launch a video game, your machine needs some time to initialize parameters and configure resources. This is why the universe needs a Big Bang. Why is the speed of light always constant? And why is it the same in every reference frame and measurement? The Michelson-Morley experiment proved that the speed of light does not depend on any medium, contradicting classical mechanics. Einstein's theory of special relativity posited that the constancy of light speed is a fundamental law of the universe, is space and time adjusting based on the observer's motion to keep the speed of light constant. Experiments and modern technologies like GPS have confirmed this again, but we still can't fully explain why the speed of light remains unchanged in every conditions. The most reasonable explanation is that the speed of light is a global constant value of a program. Every program has some parameters that are used globally, which need to be set as global constants. Not only the speed of light, but also other constants in the universe. Why does quantum entanglement exist? Two particles that are entangled and cupped are in an uncertain entangled state. When we measure the state of one particle, if its spin is up, the other particle's spin will definitely be down. The fascinating part is that no matter how far apart you spread these two particles, this non-local interaction still exists. Measuring one particle will instantaneously affect the other. This phenomenon does not require physical contact. It isn't constrained by the speed of light and isn't limited by distance, which is difficult to explain. Do you think it is so weird? But if it is a program setting, it makes sense. No matter how far apart the virtual scenarios in a program are, there are essentially just that in memory, so there is no distance between them. The time it takes to access any address in the memory is the same, and once a variable's value is modified, the program can instantaneously retrieve the modified value through a point. Why are all fermions in the universe unique? Fermions are particles with half-integer spin that obey the Pauli exclusion principle. They include particles like electrons, protons, and neutrons, and are the fundamental building blocks of matter. But by estimating the distribution of matter in the universe, scientists believe that the number of fermions in the universe is approximately on the order of 10 power 80. But can you believe that all fermions in the universe are unique? According to the Pauli exclusion principle, no two identical fermions can occupy the same quantum state simultaneously. This means that in a given system, such as an atom or the entire universe, all fermions must differ in at least one of their quantum properties, such as energy, spin, position, etc. This is really strange. If you want to create an electron right now, the the moment of its birth, the state of all electrons across the vast distance of the universe, including those beyond what humans can observe, and automatically choose a completely unique state. The only explanation is that all the electrons in the universe are produced by the same mechanism, a mechanism that generates all the electrons and tightly connects them together, ensuring that no identical electron is ever produced. Why does the observer effect exist? The observer effect refers to the phenomenon where the act of observation affects the state of a quantum system. In a quantum mechanics, a particle's state exists as a superposition of multiple possibilities when it hasn't been observed, and once observed, those possibilities collapse into a specific state. The famous double-slit experiment is an example of the observer effect. When an electron passes through two slits, it forms an interface pattern. But when a detector is placed to observe which slit the particle passes through, the interference pattern disappears, and the particle behaves like a classical particle passing through only one slit. This suggests that the act of observation itself changes the behavior of the particle. It seems as though the observer particle has consciousness and can sense that it is being observed. I was first shocked when I read about this phenomenon in a science book back in high school, feeling as if my worldview has been overturned. Later, when I became a programmer and developed games, I suddenly realized something. Those who have worked in game development know that in a game map, if a certain area is not visited by the player, the program can temporarily avoid loading that area to save resources. Only when the player actually uses that area does the program allocate resources for it. In other words, it's like a game where an area that hasn't been accessed doesn't have resources allocated to it. Only when accessed are resources assigned, saving resource in the process. When no one observes a particle, the universe server, in order to save resources, does not initialize the particle in detail. But when a player observes the particle, the server must initialize it, thus giving the particle a definite state. This explanation makes perfect sense.